So again, I'm going to start with questions. I think to this point you guys could have done, or we had assigned up through 138. So again, any questions that you guys might have at this point? Victoria. Yeah, anywhere 1 through 138 is fine. What number are you talking about? Sure. All right. Actually, that makes it easier on myself. Okay. Oh, well, there should be an equal sign there. Right, if you're looking at the problem, that just there's no equal sign between the fraction and the 4.
Oh, well, I didn't put I put.
Oh, good. Okay. All right. So first thing we do is multiply both sides by 2 to get rid of the fraction part. And the next thing I would do is multiply both sides by e to the x. So when I do that, I get e to the 2x plus 1 is equal to 8 e to the x. Cool there? Okay, I'll move that all onto one side, and I'm going to rewrite e to the 2x as e to the x squared. We talked about that last time, I think, why that was true, right? No? We can talk about it again.
Is it just like so when you get a y, it's like y squared?
Yeah.
So could you get like any of those to change into a y? How do you know which one?
Well, I want to have like something squared and then plus something else to the first and then plus a constant. So it's like a quadratic. That's the goal there. Victoria, feel okay? Okay. So solve this quadratic. We could do, well, there's 2 common ways that we'd solve a quadratic. They are quadratic formula or factoring. Now this one, the leading coefficient is 1, so you might try to factor it first, but you're going to fail pretty quick because there's not 2 numbers that multiply to give you 1 and add to give you -8. So quadratic formula it is, which always works. So 8 squared is 64, minus 4 is 60. And the square root of 60 is 4 times 15, right? And that's important because that means the square root of 50 is the square root of 4, or 2, times the square root of 15. So I can reduce that fraction like that. But we're not done because we're supposed to be solving for x, not y. So we'll go ahead and resubstitute that back out. And I wrote this as 2 separate equations because we have the plus or minus going on. To solve for x, we got to get rid of that exponent base of e. What cancels out an exponent base? a logarithm, in this case specifically the natural log, because we need the exponent base and the log base to match. Natural log is log base e. If you'd written log base e, though, that's okay. That means the same thing. And if you had typed log base e into your calculator, that's the same thing as doing the natural log. So if you forgot that, would not be the end of the world. Still get the correct answer. So I got 206 as one answer and negative 206 as the other answer.
So if the numbers match up, will you always want like the positive and negative?
Will not always be that way. If you get like your answers that are conjugates like this, they will. But if one answer was like 2 and the other answer was 5, they're not going to match up like that. It only works if they're like conjugates like that. Does that feel okay? So that's not, wouldn't always happen where they're just, the answers are opposites like that. But it can, right? Others. Again, anywhere 1 through 138 is fair game at this point. Happy to do whatever. Claire?
130.
130. Okay. So we have log of x minus 2 plus log of x plus 5 equals 2 log of 3. Okay. So the first order of business here is noticing that we have x's in 2 different locations, right? So what I'm going to need to do is work on getting those x's into a single location, or at least inside of a single logarithm. So how do I add 2 logarithms together? We have a property for this. It's the product property, right? That says log of xy is equal log of x plus log of y. Right? We're condensing. Everybody cool with that? And if I look at the right-hand side, my issue there is that I have that coefficient of 2. How can I take care of that? Use the power property. Very good. So I can move that exponent of 2 inside. Everybody cool? Now that I have log of something equals log of something else, I can just drop the logs and set those 2 somethings equal to each other. And I'm going to go ahead and multiply the stuff on the insides out while I do that. Is everybody okay with that? That's using the 1-to-1 property, or if you wanted to, you could think, oh, I'll just exponent base 10 both sides. Either way, just going to knock out the logs. So far, so good. This is a quadratic. To solve a quadratic, the first step should be it's got to equal 0. Right? What's it equal now? 9. So we'll just subtract that 9 over. And now you could try to factor this. Doesn't work. 2 things that multiply to give us negative 19, add to give us 3. So we'll use the quadratic formula. Okay, so 3 minus 4 times 1 times negative 19 is going to be 9 plus 76. So that's going to be the square root of 85. Am I done? No, what do I still need to do? I need to check, right? So remember my check, I just need to see if when I plug these values for x back into my equation, my original equation, that the number inside the logarithms has to be positive. So I'm going to convert these to decimals real quick because, well, I don't know if negative 3 plus the square root of 85 over 2 minus 2 is going to be a positive number or not, just by looking at it. But if I convert this guy into a decimal, it'll be pretty clear. So that's 3.1-ish. So when I plug it in here, I get a positive. And I plug in here, I get a positive. So that first answer is okay. If I do the second one, I get negative 6.1-ish. And if I plug that into the very first log, I get a negative. I don't need to continue checking. As soon as I get any negative, I know that that's an extraneous solution. So I'm just going to cross that one out, and I have only one answer. Claire, cool? Cool. Others? Anybody else? Okay. Well, these were good ones, guys, that you picked. Definitely some of the more challenging problems in that most recent homework section. All right. So our last section in chapter 15 is going to be talking about another application of exponential or logarithmic functions, this time into the area of finance. So that would be like banking primarily is what we're talking about here. So the primary application that we're going to be exploring in this chapter is going to be looking at interest. And there's really kind of two types of interest. Oops. When I say interest, does that mean it's like something you find fascinating? No, you silly gooses. When we talk about interest in regard to banking, what are we talking about? Okay, so there's really two places interest kind of comes up. And that's if you put money in the bank will pay you interest for keeping your money there. So some percentage of what you've been left with the bank, you will earn, you'll earn some percentage of that money back for leaving it there. The other place where interest comes up is if you borrow money from the bank is going to charge you interest on, however much of that loan remains unpaid, right? Why is the bank paying you money to keep your money in the bank? Well, what are they using your money for? They're selling it to other people as a loan, right? And if you know anything about banking, you're going to know that the interest rate on your savings account or whatever account you've invested is way less than the interest rate on a loan that's taken out. So the banks are assured to kind of make some profit by taking your money and using it to loan to other people or businesses or whatever, right? That's kind of what's going on. Like a really broad overview of like how the banking system works and why it functions. Okay. So there's kind of two different ways interest is paid or charged. Whenever I say interest, we'll be talking about both the idea of like interest that would be charged on a loan or interest that would be paid in a savings account. So the first type of interest is called simple interest. Well, let's actually not do it that way. Let's write it this way. Yeah, okay. So let's define some of this stuff. FV, we're just going to call the future value. So that would be like you invest some money sometime in the future. How much is that money now worth? Right? That's what we're saying by future value. PV stands for present value. So that would be like the amount of money you invest initially or that you take out in a loan initially. R is your interest rate as a decimal. Or I'm sorry, as a percentage. N is just the number of years. And capital I is going to be the interest earned. So depending on the question, the simple interest question, you might be using the FV equation or you might be using the I equation, right? Also, we should note that I is also going to equal just FV minus PV, right? If you take that future value and you subtract the initial investment, whatever the difference is, would be the interest that you've earned, the money you've earned from interest, right? Okay, it says if you invest $2,000 at 6% interest rate, how much total money do you have in the account after 3 years? Well, this is a simple interest problem. So we'll use the simple interest formula. What is it asking us to solve for here? Okay, and that would be which variable? That'd be the FV, right? It's a future value. Okay. What's the 2000? That's the present value, the PV. Okay. What's the 6%? It's the R, the interest rate. And then the 3 years is the N. Okay. So just plug this stuff in. So that gives us $2,360. So how much did we earn from the interest? $360, right? No big deal. Now, everything okay? Did you spill?
Yeah.
I don't have any paper towels in here right now, so you'd have to go make a trip to the bathroom to give a big scoop some up. If you need some help moving your things, I'm sure one of your neighbors would be happy to help you, like, hey, can you hold on to my stuff while I go take care of this?
I'll run and get paper towel, yeah.
No, I can get out.
Well, I'm sure that you can go too. Ben just wants to help. He's trying to be a good citizen, you know?
Yeah.
So, most of us probably have a bank account, right? I would think under your mattress, but what winnings? That's the better. Yes, of course. So when a bank actually pays you interest, are they doing it this way? No. They are not. And the reason they're not doing it this way is because it's kind of a ripoff. Because after year 1, how much money is in your account? Yeah. 120. So you'd have 2,120, right? But the interest for year 2 isn't based on that number. It's still just based on the 2,000 at the start, right? So you're never earning interest on top of the money that you earned on interest. So really, in reality, if you're being charged interest, the way this is happening is by compound interest. That's the second type. And this is a situation where you're earning interest on top of your interest. So there's our compound interest formula. So the FV, the PV, the R, and the N are all the same still as the simple formula. the difference here is we also have this K, and the K just represents the number of compounds per year. So you guys, most of you said you have a bank account. If you've noticed, when interest gets paid, how many times does that actually happen? More than once a year, typically. Typically, you get paid interest every quarter, so like 4 times a year. So that when we talk about the number of compounds per year, it's like the number of times, like some, that interest rate is like divided up, and like part of it is paid at different increments during the year. So, if it's annually, it just happens once a year. If it's semi-annually, it'd be twice. Quarterly would be like 4 times. Maybe it's monthly, it happens 12 times. Maybe it's weekly, that would be 52. Maybe you have some bonkers program where it's doing daily or 365, right? I assume that we know like how many months and weeks and days are in a year, but often I'm surprised to find that that's not always the case. So I'm just making sure that we say it at least once. So it's like, it is now, I can consider it common knowledge kind of thing, And you giggle about that, but it's like every year someone ends up asking me like, wait, how many weeks are in a year again? Weeks is the one that nobody seems to remember. All right, so let's look at an example here using our compound interest formula. It says you invest $2,000 at 6% interest rate compounded annually. How much money do you have in the account after 3 years? And we ask how much did you gain in interest? This sounds remarkably similar to the previous problem. There's one small difference that tells me that this is a compound interest problem rather than a simple interest problem. Yeah, the word compounded is the piece that I need. So that's the piece that I'm looking for to tell me that this is a compound interest problem. I think we wrote a K in. Okay, so let's start filling things in. It's asking for the total money in the account after 3 years. So what are we looking for? FV, great. So what's the PV? 2,000. Oops, forgot a 0 there. The R is? And the K is? Annually implies a 1. Yup, very good. And the N then would be 3, right? Okay, so let's rock and roll here. We can do that. 2,000 times 1 plus 6 over 100. I'm not going to put in the times 1 because, I think we all know that part doesn't really matter. Everybody's cool with that? So we get $2,382.03. So how'd that compare to the simple interest? More. How much more? It's up on the calculator. Like $22, right? Over 3 years. Is that a big whoop? Not really. Yeah, but let's look at what the difference ends up being after, say, 30 years, right? That's the question. So simple interest after 30 years, I have $5,600. Okay. Compound interest after 30 years, I have $11,486. It's almost twice as much. Whoa! So compound interest, much better deal, right? The reason that's happening, if we think about it, simple interest is like a linear function. Compound interest is like a exponential function. So the longer that time frame goes, the bigger the gap between those two interest rates would be, right? And it's not even close when it's offered at the same interest rate. The more interesting question would be like, which one is better? You know, like a higher interest rate for a simple or a lower interest rate compounding. And the answer there is like, well, it just depends on how long we're doing this for. Initially, the simple would be better, but there'd be a tipping point where after that point, the compound interest would be better for then forever afterwards. You know what I mean? But that's kind of what's going on. Everybody's okay with that? Let's look at the effect of this compounding at different amounts of time, right? So we saw that, like, you know, we had annually was 1. You know, semi-annually would be how many? 2. Quarterly would be 4. Monthly 12. Weekly would be 52. Interesting sub-question. What's bi-weekly going to be? That's every other week. So 26, half of 52. I know it's early. Why would bi-weekly often be interesting? If you're working a job, you get paid bi-weekly. Most jobs anyways. Occasionally you'll get a job that you're paid like monthly or weekly or something different, but majority of jobs are paid every other week. All right, so let's go and take our problem here, right? We saw that when K was 1, we get 2382. Let's see how that changes when K is 2. So what, about $6 difference? Yeah, all right. So if K is 4, we're doubling 2 just like when we doubled 1. So maybe this will be $12 more? No, not really. It was only like $9 more, right? It just about $3 difference in the previous one. Okay. Well, let's go make that 12 then. It's only about $2 difference, even though we tripled the number of compounds there from the previous. Okay, well, let's make it 52. That's about, like 4 times difference, a little bit more than 4, but less than $1 difference. If we make that 365, It was about 20 cents from the previous one. So again, this is better than annual, right? We're at like 23.82. So it's about $12 difference, but not a real impressive impact. You know, what's going to be a much bigger impact on how much money you're making? The interest rate itself, right? That's the thing that really is going to dictate, you know, the number of compounds per year. While that sounds really helpful and really impressive, you know, like not gonna make that much of a difference. Not like the interest rate does. All right. So we have this new compound interest formula. Let's run through some examples of the kinds of problems we can solve with this. So get some ideas on the what's going on here. So first example, we got Mara has $1,000, puts it in a saving account with 6% annual interest. Good for you for finding a saving account with 6% annual interest. Compounded monthly. How long will it take before Mara has $4,000? So again, what word do you see in here that's important? Compounded, which tells me that which interest formula I'm using. Okay. And then which of the quantities are we solving for here? Yeah, since it's how long, we're solving for the number of years, which is n. So we need to fill everything else in. All right, what's the future value going to be? The 4,000, the value we're interested in getting to. The present value would be 1,000. Great. The R is 6, and the K is it's 12 because it's compounded monthly. So far, so good? All right. To solve this equation, what should I do first? Notice where actually, let's pause. Where's the variable located in this equation? In the exponent. So at some point, what am I going to have to use? A logarithm. Everybody's good? Should I use a log straight away? No. Why not? What should I do before I can do that? I can't distribute the 1,000 through because the exponent needs to happen before multiplication. What could I do with the 1,000 though? Is the 1,000 being added? So I wouldn't want to subtract it. The 1,000 is being multiplied, so I'd want to divide it. Yes. Hey, it's okay. We're just... You want to fight? I don't want to fight with anybody. Everybody's good? Now, I could do 1 plus 6 over 120, but I'm scared of that being like a long kooky decimal, so I'm just going to leave it written that way. Victoria?
Is it 12K or 12N?
Oh, yeah, 12N. Sorry, thank you. Okay, everybody's okay? Now what? It's time for our log. Okay, log of what base should we be using? Log base log base 1 plus 6 over 1,200. Whatever that number is, I don't care what it is. Neither does my calculator. So I can type it in exactly like it's going to look on my sheet of paper. So I don't have to monkey with like converting it to a decimal and then having to round or worrying about if I rounded it too much or whatever. Okay. My last step would be to divide by 12. I'm going to write it as multiplying by a reciprocal though, because I don't want to confuse myself later if I'm looking at this and wonder, is the 12 inside the logarithm? Is it part of the base? Is it outside the logarithm? Here, if I write it this way, it's like super clear that the 12 is outside the logarithm. Is that okay with you guys? All right, so 1 over 12 times, and then math, log base, and I can type in my log base exactly how it's written on my sheet of paper. I'm not sure you can use the fraction command inside the log base, so just use the division there. And I get about 23.16 years. Okay, let's do another one. So it says, Gwen has $600 to place in a savings account. What annual interest rate would she need, compounded weekly, if she wanted to have exactly $1,500 in 10 years? First things first, what word in here is super important to us? Compounded, because that tells me that which model of interest I'm needing to use. I think we wrote a KN. It doesn't really matter. All right. What are we solving for here? Yeah, so that's the R. Okay, well, let's start filling everything else in. What is our FV? Yeah, 1,500 or 1,500 if you prefer. The PV? 600. Okay. The R is our decimal, or our variable. Sheepers, creepers. What's our K? Yes, good. So the K is sometimes tricky to pick out because it's always going to be in words like that. And then the last thing we need is our N, which is 10. Cool. All right. Where is our variable located this time? It's in the base of the exponential, right? So what are we going to need to use to solve this at some point? What do you use to solve something like that? We're going to need to use a radical. Maybe not necessarily a square root, but we're going to need to use some kind of radical here. Everybody's cool? Okay, I think so. All right, what should we do first? Divide by the 600. Yes, sir. I'm going to reduce that fraction a little bit, just to drop some zeros off of there to like make my life a little bit more convenient. Everybody feel okay there? I just did a little bit of light simplification. Not even all the way simplification, because obviously 15 over 6 can reduce more. I just didn't. I'm going to type it all in my calculator anyways. I'm just worried about reducing the digits I have to type in. You know what I mean? All right. How am I gonna, what do I need to do next? I got to get rid of that exponent, right? That 520. How am I going to cancel that out? Okay, let's return to this. How do I get rid of the exponent on the x squared? Square root, right? What if I have an x cubed? We use a cube root. If I have an x to the fourth root. If I have an x to the 520th root. So what are we going to use here? The 520th root. It's like, oh boy, that looks weird. It's okay. It's the calculator doesn't mind if it looks weird or not. Okay. What's up next? To get r by itself. Subtract 1. Yeah. Can I subtract 1 from the radical? No, so I'm just going to kind of write it next to it. And I'm going to choose to write the -1 plus in front, so I can't get confused as to whether the -1 is supposed to be under the radical or outside of the radical. If I write it that way, there's like no ambiguity. It's like definitely that's outside the radical. You know what I mean? Okay. And then my last step would be to multiply by, 5,200. Or 5,200 if you prefer. Either is fine. All right, calculator time. So 5,200 times, and then I'm going to do my parenthesis, -1 plus, and then to type in a 520th root, I'm going to type in my index, 520, press the math button, and choose option 5. So that's automatically moved the 520 into the index. If you had gone to math option 5 first, it would have just put a little blank there that you type in the 520 yourself. Either order is fine. And then I have 15 divided by 6 underneath the radical. Close my parentheses and press enter. So I need about a 9.17%. I've made one assumption along the way that's probably worth pointing out. Does anybody see what it was? That sounded thick. I'll give you a hint. Yeah, it happened on this step here. Okay, let's go back to this little piece over here. If I solve x squared equal to 4, I square root both sides, right? What would my answer be? Plus or minus 2, right? If I cube root both sides, my answer is just cube root 4. If I fourth root both sides here,
Oh, so you,
plus or minus fourth root of 4. So Landon, you see it?
you didn't include the plus or minus, because why would it like go down?
But that's okay because we know intuitively that the interest rate is going to be positive if you're getting more money. We can go automatically throw away the possibility of a negative. So you don't have to really worry about the plus or minus here, but I figured we should at least make mention of why we didn't worry about it, even though we used an even root. Is that cool with everybody? This is going to be our stopping point for today. I don't want to get into the next stuff quite yet. So you guys can do up through 155 at this point. That'll be the last stuff on this week's homework set. So this week's homework set is just going to run 131 to 155. We're going to stop here. You guys have, I don't know, 25, 30 minutes left to get started on things. Or if you have some last minute AP studying to do, like I get it. That matters too. Just try to be productive, you know, guys.